Today we are going to be going through a derivation of the Black-Scholes asset pricing model. We're going to talk a little bit about what it represents and some of the assumptions that get you there. So first off, the necessary background for this is we need to establish that we have some financial derivative. So the Black-Scholes model, it works to predict the price of some derivative. So we're going to let that derivative be represented by the function v of s, where v of s is just the payout of that derivative at a given time. And then in this case, s sub t is going to be the price of whatever the underlying is at time t. So our derivative pays out a certain amount based on it's some function of the price of some underlying thing that might be a stock or a commodity or something like that. So essentially the first step is say step, you can write in all caps, step one is going to be to model underlying. So what do we mean by model the underlying? We mean that this time t, this is sometime in the future, we need some sort of model of what we think the price might be at that time t in the future. And we know some things about the price now. So namely, we're going to say that s sub 0 equals price now. We're going to say that mu equals average return. And then we're going to let our sigma equal volatility. So already you can see some of the assumptions that are going into this model. Namely, we have the assumption that there's some constant intrinsic volatility in whatever our underlying is. Okay, and then one way that we could model this underlying is we could say, okay, we're going to have some small change in our price. That's what we're going to call VST. And we're going to equate this to, all right, so we have our two variables. We're going to say this is some percent return of the stock. So that's mu times s of t, and that's going to be times dt. So we're basically saying that this has some average return that's relatively constant with time. And then what we're going to do is, obviously, you know stocks, you know that if this is price and this is time, they don't just slope up like this. They do a lot of that. Where, yeah, sure, there might be an average return, but there's a lot of wiggling going on in between that. So how we're going to model that back in our model is we're going to add a second term that is going to be sigma dw. And what is dw? So we are going to establish over here that w of t is a Wiener process. So what is a Wiener process? A Wiener process is like if you've ever seen a, can you read that? Yeah, that's fine. If you've ever seen a random walk, the kind of thing where like at each step you're either going up one or down one, and you kind of expect that to look like some random bunch of squiggles. A Wiener process is basically the continuous version of a random walk. And the important factor in defining a Wiener process is that w of big T minus w of little t, that is going to be normally distributed with 0 as the mean, and the variance is going to be whatever your delta t is. So this basically means that in whatever time step, it adds some randomness, some random wiggles. So we're going to use this as our model for the underlying. And what are we trying to get out of this? Well, we're basically trying to get some formula st as a function of s0 and the things we know. I mean, we know mu and we know sigma. So first off, I'm going to take a step that I can motivate somewhat, but it would be something that would be difficult to come up with on your own. And that is to say that I'm going to define f of st to be the natural log of st. And why do I want to do that? Well, that's because I can write this differential df in terms of basically our differentials of st in a way that makes things really nice. So remember that for any differential, you basically are going to get a Taylor expansion here. So we're going to have that times dst, and then we're going to have plus df, the second derivative, sorry, this is going to be plus 1/2 times the second derivative with respect to st times dst squared, and then plus there's going to be a bunch of other terms. And I'm only choosing to keep these first two terms because we want our approximation to first order when we integrate. And there's a reason that'll come up soon as to why we need to keep the squared term to still approximate to first order, and it has to do with our Wiener process over here. So essentially, going over here, we're going to take this. Now, what are our derivatives of our natural logarithm? You might remember them. So we can write our df as 1 over st, because natural log of st, derivative is 1 over that, times our dst. And then this is going to be actually minus, sorry, the 1/2, or the 1/2 does come in now. I'm confused as to whether it came in from the square root. Okay, so this is going to be minus 1 over 2 times st squared dst squared. Now we can expand this out because we have a formula for dst, and that's our original model. So let's do that, and we get df equals dst, so 1 over st, and we're going to plug in st mu dt plus sigma dw, and then this is plus, there's other terms here, but we're ignoring them. So then this is going to be minus 1 over 2 st squared times this whole thing squared. And that's a little ugly. It's going to give us st squared mu squared dt squared plus sigma mu, two of those, st squared dt dw, and then finally plus, this is going to give us, what is it, st, sorry, I'm now realizing that in this original formula I was supposed to have an st here. So it's not just a Wiener process, but it's scaled by whatever our price is. Plus st squared sigma squared dw squared. Okay, so first off, we said we wanted the approximation to first order. So that means we can get rid of our squared differentials. But before we do that, we need to make one remark, which is that for any Wiener process, Wt minus W little t, that means it is normally distributed 0 to t minus t. Now, essentially, the way that I see this making sense, or here, I'll give you the formula. So it basically says, and I believe this is Ito's lemma, but our differential dw squared equals dt. You might sometimes see this written as dw equals square root of dt. I think this is ugly. I don't know why you would do that. And the way that I sort of think of this making sense is that if you take some normal distribution, you have, you can relate it to the standard normal, where it's 0, 1, and then you have to scale it by root t minus t. So you can imagine then, if we're taking some Wiener process, or if we're taking some dw, then that is basically that is basically going to be w of t plus dt minus w of t. And that, as we just found, is going to be approximately square root of dt times normal 0 to 1. As far as why, when you square it, the normal goes away and you're just left with dt, I mean, that's something for you to think about, but intuitively from here, that's how you can sort of end up with this result if you aren't able to memorize it. But for now, we are going to take it as a given. So you're going to say dw squared equals dt. That's our remark. What does that mean? That means for our formula, that means that this guy right here is just going to be dt. And now we can start getting rid of our higher order differentials. So this term, gone completely, because that's dt times dw. That would give us dt to the 3/2, which is more than 1. This term, also gone completely, because dt squared. So we're keeping these three. So we can finally write df equals, I'm going to cancel these st's, mu, I'm going to group all our dt's together. So we have mu times those cancel, and then we have another dt term over here, which is going to give us sigma squared, and then over 2, the st's cancel. So this is going to be giving us minus 1/2 sigma squared dt. And then we have our Wiener process term, which again, I forgot the st, but it's going to cancel, and you are going to be left with plus sigma dw. Now, what is the advantage to this? Because all of this, remember, is coming from setting the logarithm of st. The reason we can do this is we can say that d ln of st is equal to this thing, so we can then integrate. We can integrate, we're going to integrate from 0 to big T for now, and we're going to say that's equal to the integral from 0 to big T of mu minus sigma squared over 2 this times dt, and then we're going to say plus the integral from 0 to t of sigma dw. Okay? On this side, we're just going to have ln of s of big T over our initial price. This is good, because this is one of the things we wanted to come out of this. And then this part, we're going to have just a mu minus sigma squared over 2 times our big T, and then plus, for this part, we are going to have our sigma times w of t minus w of 0. Okay, and if you remember what we said up here, we're going to apply that here. So we're going to say, we're going to take a new variable, let y be a standard normal. We are going to say that we can replace this thing, we can replace with sigma square root of t y. Okay. And then lastly, what we want to do is we want to take e to both sides, and doing that will give us s of t equals s of 0 times e to the mu minus sigma squared over 2 times t. and then plus sigma times square root of t y. Okay, so that's that. We have modeled our underlying. So this is the first step done. You can pause here if you want to look through all of this or if anything doesn't make sense. I'm going to now erase this board so we can keep our board space for the next step. So step one was model the underlying, and the result we got out of that was s of t equals s of 0 e to the u minus sigma squared over 2 times t plus sigma root t y, with y being our standard normal PDF, or our standard normal random variable. Okay. So what do we want to do next? We have a model for our underlying. Essentially, the next step is just to model the price of the asset. So I'm going to say step 2 is derivative price. Okay. How do we come up with the price of the derivative? So you might remember that we're essentially going to use our present value formula here. So our price is going to be, remember, it's our payoff at some time, so that's going to be E of V of ST over E to the RT. E to the RT is us taking whatever time the payout will occur and weighting it backwards via present value to get the present day value of this asset. So essentially we're going to do one trick here, which is, so we're not going to be taking the normal expected value. We're actually going to be taking the risk neutral expected value. And if you haven't seen it, so basically the risk neutral expected value is something that it basically allows you to make the assumption that our R here, our R is our risk-free rate. So instead of using whatever R makes sense in whatever risky asset space you're working in, instead we can choose to use the risk-free rate R. And what that basically does is E of some function of X, where this is going to be some PDF. That's actually going to change, and that's going to be, so we'll write it like this. So here we have E to the big RT, where this is our normal present value price. We're going to say that this is equal to E star of f of x over E to the little rt, where our little r is going to be our risk-free rate. And to actually calculate what this equals, this basically changes the probabilities. So it's like as if you're saying, pretend the real PDF is not whatever your normal PDF function is, but pretend that the probability of getting a certain outcome is different in the way that makes these two the same, but lets you use the risk-free rate. We're not going to go into the details of how to do that because there's this thing that we are going to invoke for our particular situation that is called Girshanov's theorem, I believe. So essentially what we're saying is we want to find, here, I'll add a little star here. We want to find E star of V of ST over E to the RT. And remember that we actually have a formula for what S of T is, so we're going to plug that in. And we're going to say that this is equal to our formula, E to the mu minus sigma squared over 2 T plus sigma root T y. This, and then I'm going to take my E up top, keep the minus RT. Now, by what I believe is called Gershinov's theorem, we can actually take this thing and we can just say that this is equal to the normal expected value times E to the mu minus sigma 2 T plus sigma root T y E to the minus RT. Okay? And then there's one thing we need to change about this formula, and that's actually just replacing our average return with our risk-free rate of return instead. So overall, that leaves us with this. And remember this switch we made where we said y is a standard normal. We are now going to invoke the law of the unconscious statistician and just say that this, our price overall, is equal to what this value leads to. So this is going to be the integral from minus infinity to infinity. And then we're going to have our E to the minus RT out front. And then we are going to have V of S0 E to the R minus sigma squared over 2 plus sigma root Ty. Have that. And then we are going to have our standard normal PDF, which is going to be that. My apologies for this thing here. Yeah. So essentially, we have, for any underlying, this is it. This is our pricing formula in terms of whatever this function is, and we just would evaluate this integral.